Hello everyone, good afternoon. So today I'll be going over the 2019 fall exam, and then following that I will also go over some multiple choice questions from the ACS booklet. Uh, Alright, so let's start with the test. This review session might be a little bit longer than the usual because the test is longer. And yep, so let's jump in. So as usual, we're gonna start with nomenclature. Uh, Again, I like to do it by dividing them into root, subs, and then lastly we have stereo. So for the root, in this case, you have to choose the longest chain possible. So you can either go 1, 2, 3, 4, 5, and 6, or you can go 1, 2. In this case, it won't matter that much. So because they're both butyls, so it's not gonna matter, right? So we know it's a cyclohexane for the root. Oh, my bad. So it's a cyclohexane. And then for the subs, we have two subs. And remember, one thing about the subs is that you always want to start counting from the left, from the main chain out. 1, 2, 3, and 4. So for the first one, it's going to be 1, 1, 4 bromo, butyl. And for the second one, it's going to be just a 2 butyl, right? Because it's a 4 carbon, 2 butyl. Now for stereo, in this case, this one's going to be pointing down and this one's going to be pointing up. So in this case, it's going to be a trans. So to put the whole thing together, it's going to be trans. 1, 4, 1, 4 bromobutyl, and then we have 2 butyl, cyclohexane. Alright, so now moving on. A quick thing to know about double bond alkenes. When you have an alkene, there is something specific that you have to know. It's kind of a special condition is the priority of alkene and alkyne. So alkene and alkyne, they both have the same priority, but if we have the same numbering, then alkene will be on the lower numbering. In this case, there's not an example like that. But maybe I can figure out some multiple choice that can have an example like that. So anyways, again, let's do the same method. Start by root, and then subs, and stereo. So for the root, you can either start counting from, I'm gonna start with orange. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can also count in the pink method, which is the other way around. So you can start 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now if I start counting from up there, from here, 1, 2, 3, 4, 5, 6, 7, 8. So if I follow the magenta, that's more like purple. It's gonna be not the longest chain, so I cannot choose this chain, right? So it's between the orange and the pink. So let me erase the purple. So now, how to determine which one it is? If I follow the orange counting, I know I have a sub, which is the alkene on number 1. I have an alkene on number 4, and I have another sub on carbon number 4, and then on carbon number 8 I have an alkene. Now if I follow the pink counting, then I'm gonna have an alkene on number 1, a double bond on carbon number 5. Immediately, remember, you look at the first point of difference, 5 and 4, so orange will have to win in this case, right? Because you always try to find the lowest number possible. So let's erase the pink and keep the orange. So it's 9 carbons, so that's nona, right? And then it's going to be, we have 3 alkenes in this case in the main chain. So it's going to be 1, 4, 8 triene. Again, a common mistake that I see usually is people will remove the A here, won't have A. That always happens when you have like a nonene without a tri or a di, right? So just make sure you have the A here. That's a common mistake that I usually see. Now looking at the subs, we have this sub right here, which I'm going to use purple for it. So we have 1, 2. So we know that's an ethyl, but it has a double bond, so that's going to be an ethynyl, right? So, red. So 4 ethynyl. And I don't have to mark number 1 being my ene because if I don't have a number, so it's probably going to be number 1, right? Now for stereo, as we learned earlier on, that double bonds that are terminal don't have any stereo because they have 2 hydrogens connected to it, so I don't have to worry about those terminal alkenes for their double bonds. Now, when it comes to the intermediate alkenes, we have one alkene that is actually intermediate and it's on carbon 5 and 4. Why can I not erase? So it's this one. And now to be able to do that, I have to compare the groups that are connected to this alkene. Now, if I look on the right side, I have this one right here, this carbon. When you have a double bond, you should remember that when you have a double bond, it's like a carbon connected to a carbon, right? So this carbon right here is connected to 2 carbons, right? And 1 hydrogen, probably. And then this carbon is connected to 1 carbon and 2 hydrogens. So if you see here, it's the same thing as numbering. You look at the first point of difference. There's a carbon, you have a carbon, you have a carbon, you have a hydrogen. This one will have a higher priority because it's heavier. So I'm gonna mark my top one with H, representing higher priority. And then on the other side, right here I have a hydrogen. So comparing a hydrogen to a carbon, the carbon wins, meaning this one has a higher priority. So the big high priority group are pointing in the same direction, meaning they are on the same side. So it's Z. This is a good way to remember it, as I mentioned again in the test 2 review. So that stereochemistry for this structure is going to be a Z. So now let's put the name together. Again, in this case, I don't have to put a number before the Z. The reason to why is that is because there's only one double bond with stereochemistry. The other 3 double bonds are all terminal and they don't have any stereochemistry that I have to worry about. So now let's put the whole name together. Again, when you're doing stereochemistry, you start with putting the Z at the beginning of the name. So that's the Z. And then you have a 4 ethynyl. And then nona 1, 4, 8 triene. There should not be a comma here. This should be a dash. Again, another thing is that my 4s look like a 6. Like that's a complaint. So that's a 4 here. Alright, another thing that I want to mention here is that you can put these 1, 4, and 8. You can put them before, like here. I don't like doing that just because I can keep, because like you'll see next example is you're gonna have many groups in the same molecule, so it can be a little bit hard. Like if you have a triene and then an alcohol, and there it's gonna be a little bit more complicated. That's why I like putting it inside of it, right? So I can know that 1, 4, 8 is for the ene, 2 is for the alcohol, for example. I like keeping track of it, right? You can put it there. There's nothing wrong with that. This is just a preference for myself. So you're gonna see most of the time putting the numbering like that, not outside. So now moving on to number 3. In this case, we have a triple bond. So the functional groups that I have a triple bond, I have a bromine, and I have an OH. Now, the thing to know about the bromine here is that the bromine, the priority of it is really low. Like it's one of the lowest priority you'll ever see, right? So I don't wanna give you guys the list of priorities right now because that list of priorities is a little bit confusing, especially that you don't learn how to name other stuff other than alcohol and alkene and alkynes, right? So for the sake of that, just know that alcohol have a higher priority than alkene, alkyne, or alkane. Now bromine, on the other hand, they don't have any priority. Well, they have a little bit of priority, but it's not that significant. Like as of right now, for your concern, Br is the lowest priority, right? For as of right now. So, but alcohol is, as of right now, is the highest priority group you know. So knowing that, it has to be on my lowest numbering. So if I go ahead and start numbering my structure, I'm gonna have 1, 2, 3, 4, 5, 6, 7, and 8. So it's an 8 carbon. Again, let's do the root, subs, and lastly stereo. So for the root, we have an 8 carbon chain, so that's going to be an oct, right? And now we have on carbon number 7, we have a triple bond, so that would be an oct 7 wine or ine. And then on carbon 3, we have an alcohol, so that would be a 3 ol, right? So alcohol, when it comes to nomenclature, you'll just add an ol at the end. Remember, you get rid of the E here because E and O cannot be alphabetically, because they're both vowels. You cannot put two next to each other. So just keep that in mind. Now, let's look at the subs. We have one substituent in this case, and that one substituent is going to be the bromo. It's on carbon number 4, so that's going to be 4 bromo. And then for the stereo, in this question, stereo is really important. So what I'm gonna do is, just to make the picture clearer, guys, I'm gonna go ahead and erase the numbers on the nomenclature. Just go back in the video if you wanna remember the numbering, just for me to be able to put the stereochemistry and do RNS. Remember, this is a Fisher projection. In Fisher projection, the side groups are on wedges. And the groups pointing up are on dashes. So just keep that in mind. That's really important for the RNS geometry. So now, knowing that, let's start with the bottom part. The one that has the highest priority in the bottom part is going to be the oxygen, because it's the biggest group. So that's going to be my number 1. Actually, I'm going to use something else than black. Let me use blue here. So that's going to be my 1. Now, we have to look at number 2. To be able to see number 2, we have to, it's not going to be the hydrogen, right? The hydrogen has to be number 4. Now, I have to look at this carbon and this carbon right here. This carbon is connected to a carbon and 2 hydrogens, while this carbon is connected to a Br, a carbon, and a hydrogen. So the upper carbon has a higher priority, meaning that this one will have number 2 and this will be number 3. So I'm going to go ahead and erase the stuff that I wrote just for the sake of having some space so I can do my RNS. So 1, 2, 3. So that's an R. But remember, guys, when you have the smallest group number 4 on a wedge, you have to always flip the configuration. So it's going to be an R to an S. So that's an S. Now let's look at the upper one. Now, which one will have the biggest group is going to be Br, right? Because bromine is one of the biggest halides. So let me use a different color here. Let me use purple. That's French for mauve, actually, for purple. My bad. First thing first is the biggest group, as we said, is going to be Br, right? And then the lowest group is going to be obviously hydrogen. So that's going to be my number 4. Now, comparing the two, we have CH2 here and this carbon. So we look at the connections, right? So this carbon right here is connected to 1 carbon and 2 hydrogens, while this carbon right here is connected to an oxygen, a carbon, and a hydrogen. So automatically the bottom part is gonna win and has a higher priority, meaning this will be my number 2 and this will be my number 3. So now let's do the RNS. So 1, 2, 3, 4, right? That would be an S, but again, remember, it's going to switch to an R because the hydrogen is on a wedge. So let's write it down. Now, in this case, because we have 2 stereo centers, we have to put the numbering before the groups. So it's going to be 4S, and then it's going to, oh, my bad, not 4S. This one is carbon number 3. So 3s, and then we have a 4r. So let's put the name together now. Again, remember we start always by putting the stereo first of the molecule. So we have a 3s, 4r, 4-bromo, and then the root is going to be oct 7 wine 3-ol. So we covered everything that you guys know about nomenclature. Again, like as of right now, the only part that you guys know is going to be alcohol has a higher priority than alkyne and alkene. Or this is an equal sign. Are equal. Let me just write it like this. Alkyne are equal to alkene, which are better than alkanes, which mean they are better than halides. So I'm just going to put that as an X. So again, let me just emphasize that on alkynes and alkenes priority. So if you have, let me try to see if I can put it. Oh yeah, I can do that. So 1, 2, 3, 1, 1, 2. So 1, 2, 3. You have a hydrogen here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4, and then 1, 2, 3, 4. So in this case right here, you have an alkyne, you have an alkene on both sides. So you can either start counting from the right side, this side, 1, 2, 3, 4, and then 5, or you can do the opposite by starting counting from this side, 1, 2, 3, 4, and then 5. How you would decide which way to count is based on alphabetical order. And what I mean by that is, this is going to be a 5 carbon, which means it's going to start with a pent. Right? Now, if I start with the pink counting, I'm going to have pent 1. Oh, it's not pink. Pent 1 wine, and then 4-ene, right? But in this alphabetical order, you have the Y before the E, which does not work. So in this case, the priority would be to the alkene over the alkyne. So it would be pent 1 ene, and then 4 ine with an E at the end. Well, there's no E here. Anyways, I don't think that's a really good example, but I hope you guys got my point. Like, they both have the same priority, but if they're on the same numbering, the alkene has a more priority than alkyne. The reason to why is that it's just by alphabetical order. If you look at the IUPAC Blue Book, they both have the same priority. Neither of them have a better priority, except when they have the same numbering, you have to look at alphabetical priority, right? All right, so now moving on. Actually, I would like to mention that for us, like when we took the test in person, it usually felt like the final was the easier version of all the tests, right? Because she couldn't go into many details on every single topic, so it felt that they were easier. So I hope it stays this year. I just want you guys to feel a little bit better. Just make sure you know your stuff, and you guys should be good. So let's start with the facts section. Will the product of the reaction below be optically active or optically inactive? Now, what we mean by optically active or optically inactive is that for something to be optically inactive, this means that there should be a racemization, which means that there is the same amount of groups that are inverted and then that are stayed the same, right? Optically active means that all of the product inverted. So for instance, I'm going to be giving the answer when saying that when you have an SN2 reaction, all of the product are going to be inverted. The reason why is that is because the leaving group doesn't leave first, right? So however, in SN1, the leaving group leaves forming a carbon cation, and then the product can attack it from both sides. And we'll see in this example. So first of all, we'll start by noticing that this is a secondary good leaving group, and then we have a weak nucleophile. So what's going to happen here is we're going to have a SN1 reaction. So what happens here is the Br, let me just use red here. The Br is just going to leave, which is going to form a carbon cation with a positive charge. Now the CH3OH can come in and attack from either sides, either from the bottom part or it can attack from the top part. Now if it attacks from the top part, the compound is going to stay on the same geometrical configuration, OCH3, and the hydrogen is going to stay on the dash. Now if it attacks from the bottom part, what's going to end up happening is I'm going to lose my stereochemistry here. So I'm going to have a hydrogen on that, and then my OCH3 is going to be on the dash now. And this mixture is called a racemic mixture, meaning that this compound is optically inactive. So that's just some simple SN1, SN2. That's from like test 2. I think we went over the stuff. Alright, so now label the following pair as identical structural isomers, enantiomers, or diastereomers. So first thing first is that those two groups cannot be diastereomers, and the reason to why is that is, remember, for you to have a diastereomer is you have to have at least two chiral centers. But in this case, I only have one chiral center, so it cannot be a diastereomer. Now, let's see if we can see if they can be structural isomer. Remember, structural isomer is something that has a different connectivity. So, looking at this one, I have a carboxylic acid here, which I have carboxylic acid here, connect to a carbon, connect to a carbon. I have my alkyne right here, C triple bond CH, C triple bond CH is right here. And then they both connect to a carbon, which makes sense. And then I have my aldehyde, which is right here. I have that. Connect to a carbon, which makes sense. And then lastly, I have my alkene, which is right here. And it's also connected to my carbon. So it cannot be also a structural isomer because I have all of my connectivity already made. Now, to determine if they're identical or enantiomers, we have to do the RNS configuration. I mean, you can also figure out another way if you rotate it somehow. I just like doing the RNS configuration because it's much easier to be able to determine. Now, to be fair, it takes a little bit more time to do it, but I think it's a more guarantee that you get it right. So it's worth you losing 2 or 3 minutes, right? So let's start with this one. So we know that this CO2H here is like carboxylic acid, right? So we have a C double bond OOH. So to be able to see which one has the highest priority, we have to look at the biggest group. And in this case, we know that this carbon right here is connected technically to 3 oxygens, right? Because this is a double bond, indicating that's like it's technically connected to 2 oxygens. So this carbon is connected to 3 oxygens, so this one will have the highest priority. Now, this carbon is technically connected to 2 carbons and a hydrogen. This carbon right here is connected to 3 carbons. And this carbon right here is connected to 2 oxygen and a hydrogen. Now, when you're looking at this, you always look at the first point of difference. So oxygen, carbon, carbon, oxygen wins. So that will be my number 2. Now comparing this one and this side, I have a carbon, carbon, hydrogen, and the carbon, carbon, carbon. This one will have a higher priority, the carbon, 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 because it's a bigger group. So that will be my 3. And then finally, that will be my 4. So 1, 2, 3, 4. That's an S, and then it becomes an R, right? Because the reason to why is that, as mentioned before, my lowest priority group is on a wedge. It cannot be that, so we have to flip it back to an R. Right? Now, look at the other one. So, a quick thing to know, I don't know if I should explain that because, like, it's kind of a trick. But what I do usually is, because we have the same groups, it's going to be the same priority, right? So, I have a CO2H here, right? So that will be my number 1. I have an aldehyde, it's going to be my number 2 based on this reading right here, right? Let me use yellow. based on this thing right here, I said the aldehyde is gonna be number 2. And then I have my alkyne is gonna be number 3, so that's gonna be my number 3. And then finally an alkene is gonna be my number 4, so that's my number 4. Now let's do the RNS. 1, 2, 3, 4. That's an R. And I don't have to switch that because my 4 is in the plane, which technically I can just do the rotation, right? I can rotate these 3. And then I'll get my dash back on this carbon number 4. So that's an R. So we have an R and an R. They both have the same configuration, meaning that they're both identical. So I'll write here identical. All right. Consider the cyclohexane isomers below. Which isomer, A or B, would have a faster reaction in the E2 process? Remember what we mentioned? I think we went over this in test 2. Yes. So remember what we mentioned for test 2 is that when you have a cyclohexane and you're trying to perform an E2, you have to make sure that both your halide, that is your leaving group, is on the axial, and the hydrogen is also on the axial. That's also called a trans diaxial. So let me write it right here, trans diaxial. So let's draw the chair conformation of both. So to be able to have a faster reaction, right, in the A2 process, I have to be able to have my cyclohexane to be stable conformation. And as you remember, the bulk conformation is the most stable cyclohexane conformation by having the big bulky groups on an equatorial configuration. So now looking at both cyclohexanes, we notice that both have a third butyl right here, right? So I want to have those 2 third butyls on equatorial, right? So that's going to be my A. Let me just move them a little bit here. So this is going to be my A, and this is going to be my B. So looking at A, I want my third butyl to be on equatorial. So I'm just going to assume that this third butyl is here. And number that, let's pretend we number that 1, right? So now that we saw that, let's go around and add the groups. So we have on carbon number 3, we have a CH3, which is on a dash. Also, another thing that you guys have to remember is that every time it's a dash, it's going to be down. And every time it's on a wedge, it's going to be up. And remember, those are all relative, right? So if you switch, them, the wedge is down, the dash is up, just stay consistent, right? If you stay consistent, you'll get the same answer. So let's add the CH3. The CH3 is going to be pointing down, so let's pretend this is 1, 2, 3. I have my CH3 here, and I have a hydrogen here. And then my chlorine is going to be also pointing down, so that will be here, the hydrogen. And then my CH3 is also going to be pointing down, so that's a CH3 here, and a hydrogen. And that's it. So now if I look at this configuration, I'll notice that my chlorine is on equatorial. And that's not good because we cannot do we have to have both of them. That's the only condition to be able to perform an E2 on a cyclohexane, is that both the leaving group and the hydrogen have to be on an axial position. And they're not, neither of them, right? This hydrogen on equatorial and this hydrogen on equatorial. So we cannot do an E2 on this one. Well, I don't want to say we can't. We can, but it will be much slower and we'll have the less stable configuration of the cyclohexane. So now, moving to the second one. So now we know it's not A, so it has to be B, right? But let's just do it. Again, we'll do the same thing. We'll start by putting the third butyl on the equatorial right here. And then we know that this CH3 right here is going to be pointing down. In this case, down is going to be on the equatorial, CH3. And then the hydrogen right here. And then the next one is going to be a chlorine pointing down. In this case, it's going to be on an axial. And the hydrogen is equatorial. And the last thing is going to be my CH3, which is pointing down. In this case, it's going to be on an equatorial. And the hydrogen is going to be pointing up. So I have my Cl on an axial and I have a hydrogen on an axial. Actually, I have 2 hydrogens on an axial. I have this hydrogen right here. and I have this hydrogen right here. So I have both of them on axial, so that this one would work. So which one would be faster? It would be B. So now another way to be able to solve this question is by without even drawing the chair conformation, is how I like to do it is, first of all, I start by putting my biggest group on equatorial, right? Now that I chose this equatorial, every single wedge is gonna alternate. So this wedge right here with a hydrogen, there's a wedge right here with a hydrogen, there's a wedge here with a hydrogen, there's a wedge here with a hydrogen. So now what I do is I go equatorial axial around the wedges. So equatorial, this hydrogen is gonna have to be axial, this hydrogen has to be equatorial, this hydrogen has to be axial, and this hydrogen has to be equatorial. So this tells me that the Cl on the dash is equatorial. So that's a little bit faster way. You can save a couple minutes on the test. I know you guys have like 50 multiple choice question in like 2 hours, I think, 2 hours and a half or something. So it's gonna be a little bit of cram. This method always works. I've used it during Orgo 1 and Orgo 2 and always worked, like it never missed. Feel free to use it. You know, I feel like this way is much easier than drawing the chair conformation and trying to figure it out. Yep, so anyways, now let's move to the next question. Consider the resonance contributors below. Alright, place the letter of the major contributor in the box. So as we talked before, actually let me just raise these a little bit before we keep going here. So as we talked before that the stability of resonance is all dependent on the electronegativity and the stability of the negative or the positive charge, right? So if you look at the periodic table, you guys have to remember that electronegativity tends to the right, and also it's from the bottom left to the upper right, so like that. And also size plays a major role in electron instability of a positive or a negative charge. So the size goes from the top to the down, it increases in size, right? So now comparing all these three, we know that the carbon is not stable having a positive charge. So we know it's going to be the comparison between the oxygen and the S. Now, as we know, it's going to be oxygen then S, right? So we know that the oxygen is more electronegative than the sulfur, meaning that the sulfur is more stable with the positive charge, right? Because, so the S is more electropositive, in other words. So that means my C is going to be the most stable or the major contributor, right? Place the hybridization of the oxygen atom labeled A in the box. So we have this oxygen, but when there is resonance, you always want to look at all the contributors and then compare them. So if you look at this one, we have 1, 2, 3, 4. So that's an sp3 hybridized oxygen. This one right here is a 1, 2, 3. That's an sp2 hybridized oxygen. And then this one is a 1, 2, 3, 4. That's an sp3 hybridized oxygen. So now when you look at hybridization and resonance, you always want to choose the lowest hybridization number because you know that one of the lone pairs is formed to a double bond. So you always want to choose the lowest number of hybridization. That being said, it's going to be the sp2 hybridized oxygen. So it's going to be sp2. So yeah, that's pretty much it. Just make sure you know your periodic table trends, how the size and the nucleophilicity and the electronegativity change based on that, and you should be good. So like facts are that easy. I know your facts questions are gonna be like, I think I saw it being 38% of the grade or something like that. It's a huge chunk of your grade. So make sure you know your facts well, right? And you can do that by like going over her notes or like watching YouTube videos. Like Khan Academy do really good videos about facts and stuff. So nonetheless, so moving on, place the indicated bonds in order of increasing carbon-carbon bond stretching frequency, 1 being the lowest frequency and 3 being the highest frequency. So a couple things I want to mention before we move into this strength of carbon-carbon bond. So when we talk about frequency, we have to think about Gen Chem / physics a little bit. And the reason to why is because there's a specific formula that we learned, and that formula is going to be energy is equal to Planck's constant times frequency. So Planck's constant is just a constant, 6.67 times 10 to the negative 13, I think, or something like that. I don't remember really. But we know that these two, that the energy and the frequency are proportionally related. So that means as the energy increases, the frequency increases. So, and as we know in chemistry, as the energy increases, the stability decreases. And as the energy decreases, the stability increases. Just remember those trends, those are really important. And you should also know how to relate that to wavelength. We'll talk about that a little bit more later on. I don't want to guys confuse you yet, because it can be a little bit confusing. So now let's think about the carbon-carbon bond stretching. So we know that the stronger the bond, that means we need more energy to break it, right? So let me write that down. So stronger the bond, the stronger the bond, that means that we need more energy to break it, right? So that's the bond, we're breaking it, right? Like that, right? So knowing that, we know that we need more energy to break it. And if we look back at the formula, more energy meaning more frequency. So the stronger that we can conclude from that, that the stronger the bond, the stronger the bond, the higher the frequency. The higher the frequency. Can't write today, huh? The higher the frequency. So from that, we have to look back at our the structure that she gave us. Now we know that to be able to determine the strength of a carbon-carbon bond, we have to look at the S character, and the more S character, the stronger the connection, right? So knowing that, before I start comparing the bonds just based on nothing, I have to do the hybridization of every single carbon that's related to this connection. So this carbon, this carbon, this carbon, and this carbon. So this carbon right here is going to be 1, 2, 3. So that's an sp2 hybridized carbon. The one next to it, the CH2 right here, is going to be sp3 hybridized. This one is also sp3 hybridized. And then the last one is going to be sp hybridized. So now I have to look at the S character. So I know in this one, in this carbon, there is 50% S character, right? And this one right here is going to be 25%, right? Because 1/4 of the majority is S character. Same thing with this one. This one is 25%. And then the last one is going to be 33.3%, right? 1/3. So now, looking at all of that, I know I have this bond is 50 and 25. This bond is 25 and 25, is in between 25 and 25. And this one is 33 and 25. I know that the highest S character is going to be between these two right here, right? Because 50 and 25, that's 75%. That's the highest. So that would have the highest frequency, meaning that this will take number 3. Now, let's compare the last two bonds. I know that this bond right here, between these two, I have 25% and 25%, so that adds up to 50% of S character. But if I look at the last two, so these two right here, I have a 33% and 25%. So that would be higher than 50%. So that would be my second highest frequency. And this one will be my lowest frequency, right? So this is a quick way to know how to do it. I know a lot of people just memorize, the stronger the bond, the higher the frequency. I like just going through this process, because it just makes more sense, right? Like during the test, you can get caught up, you forget something, you can just figure it out, right? Instead of just trying to remember, and if you forgot it, let's say you lost the point or whatever. All right, so moving on. Place the compounds in order of increasing acidity, 1 being the least acidic and 3 being the most acidic. So we know that when we talk about acidity, we have to always, the first step that we do is, as we learned, first of all, always deprotonate, and now we can start comparing. Now, to be able to compare this, we have to look at two things, and that would be electronegativity and the atom size. And as mentioned before, we know that electronegativity increases from the left to the right, and then size increases down the periodic table. So if we have two atoms that are in the same group, the way how to compare them is we look at the size. So now we know that the nitrogen is less electronegative than both the sulfur and the oxygen. So that tells me that this one's going to be the least acidic. That will take number one. Now when I'm comparing the sulfur and the oxygen, I have to look at size. And remember, the bigger the atom size, the better, the more stable the negative charge due to the more delocalization of the charge, right? It has more room to be freely moving. So again, if you look at the periodic table, you have O and then S. So S is lower, meaning that it has a bigger atom, meaning it's the more stable in the negative charge. So that would take number 3. And then finally, that would be my number 2, because it's more stable than nitrogen, but less stable than sulfur, right? So that's pretty straightforward. Now moving to number 7, place the cation in order of increasing stability, 1 being the less stable and 2 being the more stable. So for this one, how you be able to determine this stability of carbon cation, you should know that the stability of carbon cation is tertiary, better than secondary, better than primary. And then the most stable one is going to be any of them with resonance, right? Like, for instance, a secondary with resonance is more stable than a tertiary. So, knowing that, we have this oxygen with lone pair, which can resonate, right? And then if this resonates, I'm going to end up with, and then I'm going to end up with an OH like that, with a positive charge on the oxygen. This is more stable than having a positive charge on the carbon. So because this one is resonance stabilized, so there's more delocalization of the charge, meaning that this is going to be the more stable carbon cation than the second one, right? So this will be my more stable. Oh, my bad. So that would be my more stable 2, and that would be 1. Alright, so this is the new material. Like, we haven't seen anything new yet. This is the newest things that we did not cover in test 2. So she's asking us here, is the signal for HA or HP more downfield in the HNMR spectrum of the compound below? So downfieldness, so let's pretend we have, this is our chart, the HNMR. It's gonna start from the top at like 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So the thing to know before we start jumping into like analyzing this question is downfieldness. It might look counterintuitive, but downfieldness, when she mentions downfieldness for HNMR, she means the movement to the left. So that part here is called downfield, and this part right here is called upfield. She also might call it something else, and that word would be deshielding. Deshielding. And this part would be shielding. So for something, for a structure to be more downfield than the other, or a carbon being more downfield than the other, or in this case a hydrogen being more downfield than the other, the reason to why would that be is that the electron density is pulled away, right? And that example would be something like a ketone, right? C double bond O, CH3, something like that. That causes the deshielding, right? So the electron is being pulled away, right? So this is why when you look, again, this I'm not saying that this structure is about 10. I'm just giving an example, right? So this is why a a hydrogen can be de-shielded is because the electron density is pulled away. When something is electron dense, so like let's pretend we have like an alkane, right? CH3, let's pretend. That would be in the upfield, right? To the right. So what I cannot speak. So that's what we mean by being downshielded or de-shielded. I mean downfield or de-shielded. It's something that the electrons are the electron density is being pulled away from. So knowing that, now if you look at those structures, we see that HA here, again, HA, this is a plane of symmetry, those two are the same. So if we look at HA, we have a chlorine and we have chlorine, which by induction can pull electrons away. Now carbon can pull electrons away, but it's much less, right? It's insignificant, I would even say. Now if I look at HB, it has only one chlorine and have two carbons, right? It's really small de-shield or electron induction by the carbons, but really high by the chlorine. And HA has two chlorines, meaning that this one has a high electron induction, meaning that it would cause the electrons to be pulled away from this hydrogen, meaning that this is going to be a more de-shielded hydrogen than the HB. So that the answer would be HA. Again, I'm going to go over more about these once we get to this IR and MR section. So now moving to number 9, which is also concerned with the multiplicity and H and MR, right? So answer the following question for the molecule shown below and place the answers in the appropriate boxes. For question 1, we have what are the theoretically, this is really important by the way, and we'll cover why is that. Theoretically predicted multiplets splitting patterns of the signals for the protons labeled A and B. So let's look at A first. Actually, my bad. Let's look at B first. And we'll go back to A because B is a little bit easier than A. So when looking at B, this one will have a multiplicity. And the reason to why is that is when you're looking at a group, when you're looking at H and MR, you always look at the hydrogen that are adjacent to the carbon or to the carbon that connected to this carbon. So what I mean by that is going to be this hydrogen, this hydrogen, and this hydrogen. Now another thing that you have to keep track of is the similarity, right? So what I mean by that is if we look at this group right here and this group right here, all three groups that are connected to the carbon that is connected to HB are different. Now the reason why is this important is because it will give a separate signals. And what I mean by that is that this one will have its own n+1, this one will have its own n+1, and this one will have its own n+1, right? So before I jump into that, I'm gonna assume, let me just assume that it looks something like this. CH2, we have a hydrogen here, and this is a CH2, CH3, CH2, CH2, CH3. So if you notice, I took just that part without the NH2. And the reason to why is that, and this is my HB right here. So if I look at that, I'll notice that this group and this group are the same. Meaning if I want to do the n+1 rule, I can combine both of these. So what I mean is that I can do 2 plus 2 plus 1. So that would be 5. That would have 5 peaks, right? Because those groups are the same, I just use 1 n+1. Now, in my case, the example that she gave us, you can notice that this group is different than this group, which is different than this group, again, as I mentioned before. So what tells me is that I have to do a separate n+1 for each one. So this one would have a 2 plus 1. This one would also have a 2 plus 1. And this one will have also a separate 2 plus 1. So now to be able to do all of that, I have to multiply them. So that will be a 3 times 3 times 3. So that's 9 times 3, which is 27. So for HP, I can either write 27 or I can put triplet, 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 right? I like writing 27 peaks just because it's easier, right? Now let's look at HA. Now HA is a little bit different. The reason to why is that is because there is a double bond. And that double bond plays a major role. You see, when you look at HA, this HA is syn with a hydrogen. And this hydrogen, the bottom part, is syn with this huge molecule. So this hydrogen is actually different than HA. So I have to have its own n+1. So what I mean by that is that this hydrogen will have 1 + 1, and then this hydrogen right here, because this one is the adjacent to the carbon that the hydrogen that we're looking at is connected to. So that would be also a 1 + 1. So the answer would be 4. Now let's pretend, I'm just gonna pretend that, let me see if I can just erase that, erase that, erase that, erase that, erase that. Move that a little bit like that. Copy that. Let me just add a page here. Oh well, that's not what I wanted. I'm just trying to copy that so I can just give an example. So if I were to erase this hydrogen, and instead of a hydrogen, I'm just gonna go ahead and cut all of that and have the same group being shown. That's gonna be hard. It's gonna be connected to that. That's kind of messy, but so now when I did that, those two hydrogens are the same. So if I want to do if I wanted to do the n+1 rule for this one, the multiplicity of this carbon, it would be actually a 0 + 1, which means it would be 1. And the reason why this carbon right here doesn't have any hydrogens anymore. And this hydrogen is the same as the HA. So you have to be careful by looking at if this hydrogen, the other hydrogen on the same carbon, is actually similar to the HA. If it is, then I don't have to worry about it. But if it's not, then I have to look if I have to look if it's cis to what and if I have to count it or not, right? All right, so now we know that our HA is gonna be a 4. I can also put it as a doublet. Again, I like putting 4, it's just easier. Because sometimes if you, like some people put quadra here, like a Q, that's not right. You cannot do that. It's only doublet, right? So just put 4. I mean, yes, you guys have a multiple choice, so it might be a little bit different, but. So now we have to look at the multiplicity of HC, but we have to read the question first. So under ultra pure conditions, what is the theoretically predicted multiplicity of the signal for the proton labeled C? So because she said under ultra pure conditions, this hydrogen is connected to a nitrogen. Usually, this hydrogen the multiplicity of this one would be just 0 + 1. But because she said ultra pure, I have to count the hydrogen on this carbon right here. So that would be a 1 + 1. So that would be a 2 or a doublet. And then lastly, what is the 3. What is the theoretically predicted multiplicity of the signal for the carbon atom labeled D in the proton spin coupled C13 NMR? So when we're looking at C13 NMR, it's actually, in my opinion, I think it's just the easiest, right? So if you look at carbon D right here, what you do is just you count the number of hydrogen on it, and you just add 1. So on carbon D, there's 1 hydrogen, so I just take 1 + 1, so that's 2, and will be a doublet. That's pretty much it. Right? In my opinion, C13 is the easiest, even though it's the most useless to be able to indicate a chemical structure, right? Alright, so now moving to the reaction section. Let's start with the first one. So we have a secondary BR, secondary a secondary a Br and a secondary carbon, and we have a weak nucleophile with heat, so we can know that this is going to be a SN1 reaction. So we know that SN1 reaction, the first step of the SN1, the rate determining step of the SN1 reaction, the first thing that's going to happen is the Br is going to leave, the leaving group leaves. So I'm going to end up having this Br is going to leave. Once it leaves, I'm going to end up with a carbon cation on this carbon. Now, here we have a resonance. What's going to happen? And then I'm going to end up with this resonance structure, right? It should be a double arrow. Right. Now, there is another resonance structure which is technically the same. So if you look, I come from the other side, and then I'm going to end up with this. Those two are the same, right? Those two are just equal. So, knowing that, I'm not going to go over the mechanism of how to do it, right? So, actually, let me just go over just this one, right? What's going to happen is the OCH3 H with the lone pair is going to come in, attack this positively charged. Once it attacks it, I'm going to form a OCH3 with the hydrogen here. Now another OCH3, OHCH3, is going to come in and grab this hydrogen, and I'm going to end up with one of the products, OCH3 being here. Now for the other product, I'm going to form the same thing, but now this time the OCH would be at the end, so it will be for this one. So it looks something like that, OCH3, and there's a double bond here and a double bond right here. Wait, no, double bond here and double bond right here. Pretty straightforward, just normal SN1 from earlier this semester. Alright, so now let's move on to the new reaction. So the first part, so those are multi-step reactions. Those multi-step reactions, when the test was in person, we had to draw every step, like 1, 2, 3. And even though this time the test is gonna be it's gonna semi-online, right? I think the best way to solve those problems is also do it the same way, right? Draw every single reaction separate, right? That's at least what I think. Right? It helps you keeping track of everything. So the first step of the reaction, it's going to be OSO4 with peroxide and OH minus. This reaction will add a syndiol in between this alkene. So what I'm going to end up having is, I'm going to have this CH3 on a wedge, let's pretend. And then the two OHs are going to be on a dash because they're syn. Now the second step is going to be HiO4. Now, there's a quick way to remember this one. It's kind of silly. HiO4, if you read like it's haya, it's like karate. So you can like break it in between the two OHs, the two alcohols. And once you break it, you're going to form a double bond O instead of the OHs. So how would that look is, let me pretend that I have 1, 2, 3, 4, 5, and then 6. So that's a 6-member ring. So that would look something like that. Right? 1, 2, 3. On carbon number 3 right here, I'm going to have a double bond O. And on this one, I'm going to have a aldehyde. And on carbon number 6, which is going to be this one, I'm going to have just a ketone with double bond O. So what I just did, I just split it in half and convert the alcohols into ketones or carbonyls, right? Not ketones, right? Into carbonyls. C double bond O, C double bond O, and I left everything the same. Now the third step is going to be Na2Cr2O7, which is also known as Jones reagent. And what this one does is a strong oxidizing agent, and it oxidizes everything. It oxidizes alcohol all the way to carboxylic acids. It oxidizes aldehyde all the way to carboxylic acids. It cannot, but something to keep in mind is tertiary alcohol cannot be oxidized, right? So in this case, the only thing that can be oxidized that's left over is going to be the aldehyde, because this double bond O is already oxidized all the way, right? So this Jones reagent is going to oxidize the aldehyde all the way to the carboxylic acid with an OH right here, with a double bond O here. And now the last one is NABH4. NABH4 is a mild reducing agent, and it can only reduce two things, and those two things are gonna be ketones and aldehyde. Aldehydes? I don't know, but I think it spells like that. The other one that is a strong reducing agent, I don't think we're gonna see on this test, but a strong reducing agent is Allylic. This is a strong reducing agent. It reduces everything. It reduces carboxylic acids, aldehydes, ketones, everything. So in this case, after mentioning that we'll be able to reduce only the aldehydes and ketones, so it will be able to reduce this ketone, but not this carboxylic acid, because it's not strong enough. So I'm gonna end up with this, no H, and then from the other side, I'm just gonna keep the carboxylic acid, double bond OOH. Alright, so now moving on, we have this structure, and if you guys remember, this is a strong, bulky base. So this is a bulky base, and now we have a tertiary bromine. So this is gonna be an E1 reaction, and remember, in an E1 reaction, it's like SN1. What happens in the first step is that the Br group is just gonna leave, and we're gonna end up with a carbon cation. In this case, it's a tertiary carbon cation. Now that we formed the carbon cation, we have two possibilities to take the hydrogen and form a elimination reaction. We either have this hydrogen, the blue one, or we have the purple one, this hydrogen. So because we mentioned that this is a bulky base, we know that because it's bulky, it's going to take the hydrogen that is less steric. In other ways, it's going to form the less substituted alkene, right? So for the major product, this base is going to come and grab the hydrogen and form the double bond, and I'm going to end up with a double bond right here. So that would be my major, and now for my minor, it's going to go into the more steric hindered hydrogen, grab the most steric hindered hydrogen, or the blue hydrogen in this case, and you're going to end up with this product. Also, another thing that I should mention is that this hydrogen and let me just use a different color here, and this hydrogen right here, those two are the same just because there's this plane of symmetry in the middle, so those two are just the same, right? So that makes sense. So now moving on. So for this one, we have a CH3-MgBr, which is a Grignard reagent with a carbonyl carbons, but this time it's an ester. It's a little bit different than what we used to see, right? So what happens is, I'm gonna draw a little bit of mechanism here. You're not supposed to like draw mechanism in this section, but I just like to do it so we can get a better understanding of the reactions that we have to know the mechanism of. So pretty much this is one of the most important mechanisms that you guys have to know. This is such an important reaction is because once I get into synthesis, you'll guys see why. And the reason why is that is because you'll be able, using Grignard reaction, you'll be able to form this carbon-carbon bond, and I'll get deeper into this discussion later on. So we know that this CH3-MgBr is going to act as a nucleophile. The reason to why is because this one is partially negative. This carbon right here is partially positive due to the induction by this oxygen, right? So what's going to happen is this negatively charged bond is going to come in and attack this oxygen. Once it attacks it, the pi bond is going to form a lone pair on the oxygen, and this is one of the intermediate steps that's going to happen is it's going to be an O minus, and then you have a CH3 right here. Now the next step to what's going to happen is this negative charge is going to come back down and kick off this oxygen. And now what's going to happen is you're going to end up with this structure, O minus right here, and then you have a double bond O and a CH3. Now, because we have an excess of CH3 and GBr, the next step that's going to happen is another Grignard reagent is going to come in, attack this carbonyl carbon, kick off the electron, and then you're going to end up forming this thing. An O minus and then you're gonna form that with an O minus, and then you have two CH3s here. Now, if you notice something, there is a then here. This then is really important to have. If this then wasn't there, then this reaction would never occur. And you should keep that in mind when you're doing synthesis. Those two reactions should be separate by something, either one and then, or you can put one CH3 and then two H3O plus. That's really important because if the H3O plus and the linear reagent was present at the same time, those two would react to together, right? This is acidic, this is a partial negative charge, they will react together and reaction won't occur. Actually, when we took the lab in person and we had to do this reaction, we had to dry everything out of water, right? Like we used a heat gun to clean out, like to dry all the stuff that we're gonna use before the reaction. So now that we formed that, the next step is gonna be H3O plus. So what's gonna happen is gonna just protonate those O minuses. So I'm gonna end up with this in OH, CH3, and there is no H here. So now the last step is going to be HBr ethane at 0 degrees Celsius. As you remember, this reaction goes from an OH to a Br, but this reaction only works for tertiary alcohols. It won't work for secondary, it won't work for primary. Just keep that in mind, that's really important. So you're going to end up with that, and there is an OH here. And then from the bottom part, there is 1, 2, and then there's a, instead of an OH here, then you're going to have a Br. Is that the right number of carbons? 1, 2, 3, 4, yeah. So that's pretty much the reaction. So this is an important step because this is an important reaction because it's like combines a Grignard and like an ester, which is really an important reaction, I think. Alright, so now moving on to the next reaction. So we have H2SO4 and heat. This H2SO4 is gonna form a dehydration reaction. So what's gonna happen is this lone pair on the oxygen is gonna come in, grab the hydrogen from the H2SO4. So you're gonna form that. OH, that's positively charged. This H2O is now a good leaving group, so what's gonna happen is it's just gonna leave. Once it leaves, it forms a partially positive charge. And what's gonna happen is this can do a hydride shift, form a tertiary carbon cation, and then after it forms a tertiary carbon cation, the SO3 minus is gonna the SO4 minus is gonna come in, grab the hydrogen and form a double bond. So I'm not gonna draw this whole mechanism, I'm just gonna form the double bond. But just remember, when you're using H2SO4, it's going to form the more substituted alkene. That's an important step to know. You should know the mechanism of the dehydration reaction. It's really important. Now, the next step is going to be Br2 and H2O. So what's going to happen here is going to add the Br and an OH in a N-type position. And it's also in a mark addition. So the OH will go to the more substituted carbon. So that would mean here. And then the Br is going to, I should not say it's going to act like the hydrogen, but it's going to go to the less substituted carbon. So it go right here. So those are pretty straightforward reactions. So now, moving on to this reaction. This is an NH2, so that's a strong base. Not only strong base, that's also a small strong base. And remember, when you have cyclohexanes, you gotta always think about this trans diaxide that we talked about earlier. So again, I'm gonna use my wake method in this case. I don't want to draw the chair conformation. So the first step that you guys want to do always is indicate the biggest group on your cyclohexane with an equatorial. So I know that this guy is gonna be equatorial on a dash. This means that this CH is axial, this chlorine is equatorial, this dash right here, hydrogen, is gonna be axial. This hydrogen right here is going to be equatorial, but the chlorine is axial. And this dash right here, hydrogen, is going to be axial. And this CH is going to be equatorial. So remember, it's trans diaxial. So the only chlorine that I can use is going to be this chlorine right here because it's on an axial. and I want my hydrogens to be on axial. So both hydrogens are going to be on axial. Now, to be able to determine which one's gonna be the hydrogen that I use is based on the bulkiness of the base. As we said, this is a small base, so the major one is gonna form the more substituted alkene. So to form the more substituted alkene, we have a CH3 right here, a CH3 right here, we have a Cl right here, and that's gonna be my more substituted alkene. Remember, the reason to why my more substituted alkene is the more stable or the major is because it's a small, strong base. Now for my minor, it's gonna be the less substituted alkene. So that would be this one, the double bond here, right? I got rid of this hydrogen this time. And then I'm gonna have my CH3 here. I'm gonna have a terbutyl. I'm gonna have a CH3 right here, and a Cl here. That's pretty straightforward. It's all just from the old test. That's from earlier chapters. All right, now moving on. So first reaction, we have an alkene with a Br2CCl2 or CH2Cl2. So this reaction, you're gonna go from the alkene to a vicinal bromine, and that vicinal bromine have to be in anti-positioning. So what's gonna happen is I'm gonna get rid of this alkene. I'm gonna have a Br up and Br down in an anti-position. That's really important. And again, so if you get stuck on one of the steps, that's what I tell all my students. So if you get stuck on one of the reactions, what I do usually in my when I took the class, I usually look at the second reaction, right? So I have NaNH2 with 150 degrees Celsius. I know that we go from either vicinal or geminal halides to a triple bond, right? So I can tell that my first reaction has to form somehow a vicinal or a geminal bromine. So I can just guesstimate, I would say. I don't want to say guess, it's more like guesstimating. So the second reaction that we will talk in a little bit, so it's NaNH2 at 150 degrees Celsius. So this type of there are two types of reactions that can go from a vicinal or a geminal halide to a triple bond. There's NaNH2, which is this one, NH2 at 150 degrees Celsius, and the other one is going to be KOH at 200 degrees Celsius. Now, the difference between these two is that NaNH2 at 150 degrees Celsius, you're going to end up with a terminal alkyne, but KOH at 200 degrees Celsius, you're going to end up with an internal triple bond. The way I remember this one, you do not have to know the mechanism of what happens. It's a little bit complicated. That's why Dr. Bean doesn't go over it. So she goes over the general mechanism of how the base can form a triple bond, right? But for me to remember which one is which, so 150 degrees Celsius is cooler than 200 degrees Celsius, right? So 150 degrees Celsius is cold, I would say. I don't want to say it's cold. 150 degrees Celsius is really hot, actually. But 150 degrees Celsius is cold comparatively to 200 degrees Celsius. And outside is cold, so terminal is 150 degrees Celsius, and then 200 degrees Celsius is internal because inside is hot. So that's a quick way to remember. And also another thing that NaNH2 forms, NaNH2 without anything, it will, NaNH2 with 150 degrees Celsius, you're gonna always end up with a terminal negatively charged, right? And then you have to add then H3O plus. Just keep that in mind because this is really important, especially in synthesis. This is why here she put the then H3O plus. You see that? So without that then, let's pretend this is step 3 and then this is step 4. Just for the case of learning. So as we said, the NaNH2 is gonna end up with a terminal triple bond. Also, another thing that I should mention is that when you're drawing triple bond, make sure that, you're not, I keep forgetting that you guys have it online. Anyways, what I'm trying to say is when you're trying to draw a triple bond, make sure it's flat, because remember, it's sp hybridized carbons, which means it's at 180 degree angle. So just keep that in mind. So you have a C triple bond CH. Oh, well, I'm sorry, I forgot that we're splitting them. So step 2, you're gonna end up with a CH2C, C triple bond C minus. And then step 3, because any NH2 is a base, right? So even if you form a CH at the end, it's gonna come back and deprotonate this hydrogen. And then the last step is gonna, not the last step, the third step is gonna be CH2, C triple bond C hydrogen. And the fourth step, which is HgSO4, H2SO4 / H2O. In this step, what's gonna happen is you're gonna form a ketone. And the way I remember them, there are 2 reactions that you should be familiar with the formation of a carbonyls with triple bond, and the other one is going to be SiABH2 and stuff with it, right? Cia, you should remember that Cia forms an aldehyde, right? And the way I remember it is Hg, mercury is like Markov-Nikov, right? It's going to add a double bond O to the more substituted carbon. I don't know if that's helpful. I remember it this way. It's kind of helpful for me because, again, you don't have to know the mechanism for this one. It's really complicated. So I'm going to end up with a ketone here, CH2, C double bond O, CH3. So that's step 4 in my case here. Alright, so now moving on, NBS and line. As we know, NBS and line will form a radical on an allylic position. So here you have to determine which allylic position, right? You have this allylic position, you have this allylic position, you have this allylic position, and you have this allylic position. In these 2 allylic positions, it's not possible because this carbon does not have any hydrogen to form a radical. So those are out of the picture. And these 2 allylic positions are actually the same, right? Because there's a plane of symmetry in the middle, so those 2 are the same. So I'm just going to choose one of them and just draw it on based on that. So if I draw the radical, I'm going to form a radical right here. Now, once I form this radical, if you notice, I have a resonance contributor that I can draw, and that resonance would be something like that. I'm going to form a radical right here, and then the double bond moved all the way to here. So now, wherever I form those radicals, I'm just going to add a Br. So for the first one, I'm going to have a Br right here, and a double bond here. And then for the second one, I'm going to have a double bond right here with the Br right here. So it's just the old reactions. It's a little bit complicated because you have that resonance contributor in it, and that can form another bromine. So now moving on, we have an alcohol with a PTCl. So a good thing to know about this is that this one will form an OTOS group, and that OTOS group is gonna keep stereochemistry. So if I look at this one and try to form this OTOS group, it's gonna be on the wedge. So whatever the stereochemistry is, it's gonna stay. And why are we doing OTOS? Is because OTOS is a good leaving group. And then the hydrogen on the dash. And now the second step is going to be CH3S-, which is going to act as a strong nucleophile. And then because we have this OTOS is a good leaving group on the secondary, meaning that we can just do an SN2 reaction, right? So 2. And remember, in an SN2 reaction, there is an inversion that occurs. So that means that my SCH3 and then my hydrogen is the on the wedge. So that's the final product. All right, now let's look into mechanisms. So in mechanisms, I don't think you're gonna have anything like that. She's gonna probably ask you like concept questions for mechanism, right? So anyways, I think this is a really good mechanism because it has almost everything that you're gonna see for mechanism as of right now. So first thing first is you have alcohols and you have a acid. So we saw this reaction earlier on, and we said that this reaction is a dehydration reaction. And what occurs in dehydration reaction is that the first step is going to be that this oxygen has a lone pair, which is going to grab a hydrogen, and that would end up with no H. I mean, an H2O, I mean. Right, with a positive charge. I know some people, when they look at mechanism, they look at the product. I don't think the first couple steps is gonna help you anything with the products, right? Maybe later on, but as of right now, I don't think it's kind of useful to look at that. So what's gonna happen here is that this H2O is gonna act as a good leaving group, and it's gonna leave, and you're gonna end up with a carbon cation. OH here. And then, oh, my bad, this leaves, so then there's be a positive charge here. And then I'm going to draw this hydrogen here because there's something that we should notice here. So we notice that we have a tertiary carbon cation, but Danny, like, tertiary carbon cation are the most stable. Why would it want to move somewhere, right? There will be a hydrogen shift here, because if you notice, if I move this, if I do a hydride shift here, I'm going to end up with a positive charge right here, which is adjacent to an oxygen, which means that I have resonance. And remember, resonance is more stable than tertiary, secondary, or even primary, right? So if I were to do this hydride shift, I'm going to end up with a hydrogen right here, and then I have a positive charge, and then NOH. Now this oxygen has two lone pairs. One of the lone pairs is going to contribute and form a double bond. I'm just drawing the resonance here, right? So going to form a double bond OH. So now I have the positive charge on the OH, which is even more stable. Now at this point, I want to start looking at the product, because like I don't know where to go from here. So I know my product is this one, so I'll just have to deprotonate this oxygen and I'm good, right? So what I can use here, let me see, I can use O minus SO3H, right? Because I deprotonated this acid later on, earlier on. So it's gonna grab this hydrogen. Once it grabs it, it's going to kick off the electrons back to the oxygen, and I'm going to end up with this group right here. So that's this one, right? Those two are the same. Now to do the other product, like looking at this one, I cannot really do any hydride shift here, right? So or not a hydride shift, any ring opening, right? Because like even if I have this positive charge right here, I'm gonna open it. It's gonna be a little bit complicated, but what I can do is I can use the other alcohol and protonate this alcohol. So let's look at that. Let me use a different color here. So let's use pink. So this oxygen now is gonna grab this hydrogen, and then this is gonna kick off here, and now my structure is going to look something like that. So I'm going to keep this OH here, and then I'm going to have that, and then H2O right here with a positive charge. Now, as we said, H2O is a good leaving group, so this is just going to leave. Let me add a page, actually, because this is getting too complicated here. Too crowded, not complicated. That's not that complicated. So once this leaves, I'm gonna end up with a positive charge. And then there is no H right here. Now we know that we're gonna have a ring opening, right? So this is the perfect time to use a ring opening. So how I like to do ring openings is by numbering, because I think this is the easiest way to keep track of everything. So what I like doing is I like just numbering 1, 2, 3, 4. Let's pretend this is 5. So the reason why I'm numbering this way, because I know I'm going to have to open the ring like this, right? So if I go around, it's going to be 1, 2, 3, 4. This is going to be my square that I'm going to form, which is going to be this thing, right? This is how I like to do it. If you have a better way of thinking about it, you should use it. Like, there are so many ways that people do ring openings. I'll just like it this way because I can keep track of everything. So 2, 1, 2, 3, 4, right? So this is gonna be my carbon number 2. So now I go ahead and number them again. So 2, 1, 3, and 4. So now I know carbon number 4 is connected to a carbon which is connected to 2 things. So it would look like that. Carbon number 1 is connected to an OH. And now my positive charge, if you look at my positive charge on carbon number 4 and then look at this carbon number 4. This carbon number 4 was connected to 1, 2, and there's a hydrogen here. And now this carbon number 4 is connected to 1, 2, 3, and a hydrogen. So this carbon doesn't have a positive charge anymore, right? It doesn't need it. It's 4 minus 4 is 0. There's no formal charge here anymore. But if I look at carbon number 1, which is right here, this carbon, and I compare it to the previous one. Look at this one here. This carbon was connected to 1, 2, 3, 4, right? Now this carbon number 1 is connected, has one connection with the OH, one with this one, one with this one. So it has 3 connections. So 4 minus 3 is a plus 1. And now I have a resonance structure. This O right here is going to kick off this electron, and I'm going to end up with a double bond O, H, positively charged, and then this one's like that. And now O minus SO3H can come in and grab this hydrogen, and I'm going to end up with the product that I need. So is that it? Let me check. Yep, so that's it. That's it. So it's pretty straightforward. Just make sure you keep track of everything and you should be good. I don't think it's anything complicated. The complicated thing about mechanism is just keeping track of everything, right? This is why I just like using numbering, like here, you know, so I can keep track of stuff. But if you have a better method that you feel like you're more confident with, just go ahead and use it. Like, there's so many ways you can, like, there's only one way that the electron movement, right? But there's so many ways to, like, keep track of everything. So if you have your own method that you feel comfortable with, you should go ahead and just keep using yours, right? All right, now let's jump into synthesis. So first thing you want to do when looking at synthesis, you want to see what your starting product are going to be. Now, I know on your test you're not going to have any synthesis questions, but I think this is even like good practice. You're probably going to have like reactions without the reagents. So like you're going to have the starting reactant, and you're going to have the final product, and you'll have to like draw the intermediate. So it's technically a synthesis, right? So what you want to do first up is determine what are your beginning reagents. So she said you can use a cyclohexanol, so something like that. Let me use the red just because it's clear to see. You can use a cyclohexanol, any alcohol or alkenes of 4 carbons or less. So 4, 1, 2, 3, 4. 4 carbons or less, any organic reagent, any peroxy acids, or any oxidizing or reducing agents. So this stuff is kind of new to you guys, like compared to the last time. Peroxy acids is something that like forms an epoxy, like MCPBA, stuff like that. Oxidizing, like Jones reagent. Reducing is NABH4 or LiLH4, right? Those are the reducing or the oxidizing agents. So now the second step, what you have to do here is you have to try to notice what functional group you have. So as we look here, the only functional group that we see is going to be this ester group, right? The C double bond O connected to an oxygen. You always want to try to split the molecule, or well, form the molecule at this functional group. So if I split it right here, and I can do, if you guys remember, towards the end of her notes, she mentioned something about Fischer esterification. And that Fischer esterification As of right now, you don't have to know the mechanism of it. You'll learn the mechanism later on in organic chemistry too. But as of right now, you should not worry about it. But what you do to form this ester is gonna be a carboxylic acid and an alcohol. So this is gonna be the carboxylic acid part that you're gonna form, and this is gonna be my alcohol that I'm gonna form. So it's gonna be a cyclohexane with a CH2, C double bond O, OH, plus a carbon right here, connect to 1, 2, 3, connected to 1, 2, 3, 1, 2, 3, and then there's an OH right here. And the reagent that you have to use is an acid. And again, I don't want to go into details, but what happens is that one of them is going to get protonated, and then it's going to act as a good leaving group. Again, I'm not gonna go into many details because you don't have to know this, but just you should know the name of the reaction is going to be Fischer esterification. Fischer esterification. Now to form this carboxylic, I'm gonna try it from the left side first. So to form this carboxylic acid right here, you need to oxidize, start with an alcohol, right? So we can use Jones reagent. Jones reagent. Remember, Jones reagent something is like Na2, Cr2, O7, H2SO4, and H2O. So what happens is, I'm going to start with an alcohol, and that's going to oxidize all the way to a carboxylic acid. So that would look something like that. A CH2, CH2, and then an OH. Now, remember what we mentioned is that we have to start with a cyclohexanol and 4 carbon or less. So we have a cyclohexane here, and we have a 2 carbons. So I want to try to split it right here. And the only reaction that we know how to do that is using Grignard reaction. So what I can do is, if I use Grignard reaction using MgBr and the aldehyde, it's going to be a little bit hard, because what's going to happen is I'm going to have to form something like this first, CH2, MgBr, and attack it with the C double bond OH, and then repeat the process twice. Instead of doing that, there's an easier way to do that. So I'm gonna use an epoxy, and you'll see why that would be. Now you can do what I just drew, but it takes a little bit more time. So what I can do is, I'm gonna have the MgBr right here, and then use an epoxy. Right? And then remember, this is going to act as a nucleophile. It's going to come in right here, attack this, and kick the electron back to the oxygen, forming the OH. And you always want to have this then here, because remember, you cannot have H3O plus in the reaction, because it will react with the MgBr and the reaction won't occur. That then is worth like 2 points when I took the test. Right? So that's really important to keep in mind. Now let's form this epoxy. We can just use MCPBA. And because we didn't see this reaction earlier on, I think I'm going to draw the structure of MCPBA. MCPBA is gonna look, it's metachloroperoxybenzoic acid. So it looks something like this. It's a benzene ring with a chlorine. We have bond, oxygen, and then OH, I think. So metaperoxybenzoic acid. Yeah. So this is how it looks like. You should know the structure. You should keep in mind the general structure of it at least, because again, it's multiple choice, so she can like give you the structure of it instead of just the name, right? And then remember, when we do MCPBA, we always start with an alkene, so that's a CH2 double bond CH2. And now to form the MgBr, first of all, it's going to be Mg ether, right? And then that would have a Br right here. And then for the last step, remember, I cannot start with a cyclohexane, I have to start with a cyclohexanol. And to do that, I can use PBr3 here with an alcohol. I cannot use HBr at 0 degrees Celsius and ether because it's only for tertiary. So you gotta be able to tell the difference. So that's my beginning product for this one, and that's my beginning product for this one. And they both are, okay, this one has less than 4 carbons, alkene, and this is cyclohexanol, so I'm good here. Now let's look at the other part. For this one, again, I want to try to break this carbon-carbon bond, and I'm going to try to break it right here, right? And the only way that I can form a carbon-carbon bond is by using a Grignard reaction. So I'm going to use a cyclohexane with an MgBr plus I should have a carbonyl. So instead of this alcohol, I'm going to have a carbonyl. My bad. 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7. And I have a carbonyl right here. Now, I already made this one, so I don't have to worry about it. So I can just say I already made. Now for this one, again, I cannot, this is a 1, 2, 3, 4, 5, 6, 7 carbons. This cannot be my final product, right? So first of all, let me form an alcohol so I can break further on this carbon-carbon bond. So let me just use Jones. I can also use here PCC reagent. And you guys should know the difference between Jones and PCC. When you have a primary alcohol, Jones reagent is going to take it all the way to a carboxylic acid, while PCC will take it all the way to an aldehyde. This is a big difference between those two reagents. So, but as a secondary alcohol, it's not going to matter because they're both going to go to a ketone. So that's going to form this thing with an OH. Now I can do a carbon-carbon bond. I mean, form a carbon-carbon bond because we're going in reverse, not break, right? So let me just use a different color here so we can guys see it. So now it's gonna be 1, 2, 3 with an MgBr plus a 1, 2, 3 with a double bond O. 1, 2, 3. Let me draw it this way. 1, 2, double bond O. 1, 2, 3. 1, 2, 3. Oh, actually that's 4 carbons. My bad. 1, 2, 1, 2, 3, 4 double bond O, and then the hydrogen. So let's form this thing first. So I'm just gonna use, first of all, I'm gonna use Mg and ether. So that would be a Br here. And then to form this Br, remember I cannot start with Br2 and light because I have to start, well, I can start with an alkane. Oh, my bad. I can start with an alkane, but the thing, can I start with alkane? 4 carbon alkenes or 4 carbon. Oh no, I cannot start with an alkene. I can only start with an alkene or an alcohol. So I have to use PBr3 here with an alcohol, an OH right here. Now to form this aldehyde right here, actually let me add a page so we don't have it crammed in there. So to form this aldehyde, I can start with a primary alcohol. 1, 2, 3, 1, 2, 3. Oh, 4 carbons. Oh, I keep messing this up. 1, 2, 3. No H right here. And now I have to use PCC because if I use Jones reagent, I'm gonna end up with this product. 1, 2, 3, 4. And that's not good. That's not what I want, right? I want an aldehyde. So for primary, you have to notice if you use PCC, you're going to end up with an aldehyde. But if you use Jones reagent with a primary, you're going to end up with a carboxylic acid. PCC is a weaker oxidizing agent than Jones reagent or KMNO4 warm, right? So once I use PCC, I can start with an alcohol. So that would be my final product. So 1, 2, 3, 4. 4 carbons of alcohol and alkene. 3 carbons of alcohol alkene. So they're all good. So I'm good, and that's pretty much the synthesis, right? I know you're not gonna have a synthesis problem on the like this one. At least you're gonna have probably a reaction without reagents, so you have to write the reagents in there. That's technically a synthesis, right? All right, so now let's move on to the last problem of the free response before we move on to the multiple choice questions. So when you get hit by, when you see a spectroscopy problem, always the first step, always, and that's like a rule of thumb, you always want to start with calculating the unsaturation number. So And as you guys remember, it's 2 times carbons, number of carbons, plus 2 minus the number of hydrogens divided by 2. So in this case, it's going to be 2 times 10 is 20, 22, minus 12 divided by 2. So 10 divided by 2 is going to be 5. You're not going to be allowed a calculator on the test. It's just simple math, right? It's nothing that's really complicated. Just make sure you just do it one step at a time and you'll be good. Now let's talk about this 5. This is a huge unsaturation number. So when you have an unsaturation number 4 or bigger, you probably have a benzene ring, right? A benzene ring has an unsaturation number of 4. And the reason to why is that because it has three double bonds and 1 ring, so that would add up to a 4, right? So in this case, this is telling me that there is a benzene ring and there's a double bond. Now let's look at the compound. We have C10H12O2. We have 2 oxygens. Let's first of all look at the IR spectrum. So first thing first, about 1500, anything after that is just fingerprint. You cannot tell anything from it. Some people look at it to find ethers, but it's really hard. And even Dr. Bean says not to look at after 1500-ish because it's kind of hard to see anything after that. But now we see one thing. Those bonds right here, those stretches are just CC and CH bonds. That doesn't help us with anything. The only thing that jumps out of the IR spectrum is going to be this strong peak at 1700s. This strong peak at 1700s tells us that there is a carbonyl. So now we know that the double bond is going to be a carbonyl. But if you notice something, you have 2 oxygens. Now we know it's not an alcohol because if it was an alcohol, then we'll have a 3300 stretch, right? A wide 3300 stretch. So the only thing that's left, right? It's not a what's it called? It's not an alcohol, right? We only have 1 carbonyl, right? It might be 2 carbonyl. I mean, it cannot be 2 carbonyls because we only have 1 double bond. So the only other option is gonna be like an ether, right? Bond O bond, right? So let's look down to the H NMR. Now, this is how I like to do this one. So first of all, I look at this one. So that's CH3, right? So that's a CH3. And then I look at the peaks. This one has 3 peaks, which means connect to ACH2. Now this one has a 2H CH2, which is connected to 1, 2, 3, 4. So that's a CH3, right? So these 2 complete each other, right? Now let's look at this one. Look at this one right here. This is a CH2 connected to a 1, 2, 3, which is connected to another CH2. If you notice something about this one though, right? Don't you see something really weird about this one? Look how downfield this is. Right, and as we mentioned before, this downfieldness is due to the like unequal distribution of negative cloud. And we'll talk a little bit later about this one. So, and then lastly, if you look at those 2 peaks here, 2H and 3H around 7 to 8. This always represents an aromatic ring. So let's add these 2 together. You'll have a 5H. And you should guys know that a benzene ring has normally 6 hydrogens. Because this one has 5 hydrogens, this tells you that this one is going to be monosubstituted. Now, if this one would have added up to a 4H, that would have been a di-substituted benzene ring with a para positioning. Para is just opposite to each other, right? Top and bottom. But this one is 5H. So that tells me it's monosubstituted. So now, how I like doing this is I like always starting by just guessing something and then going from there, right? So let's draw the benzene ring. Right, I know I have a C double bond O, right? And I know that I have a bond that's connected to an O, right? And I also know that I have a CH2, CH3, CH3, right? CH2, CH2, CH3. So what I would do here is I would put the whole thing together. But there's something to notice here, is that this CH2 has to be connected to like an oxygen or something. The reason to why is that because it's way downfield compared to normal alkanes, right? So because of that, I'm gonna connect this oxygen to the CH2. So I'm guessing it's gonna be C double bond O, oxygen, CH2, CH2, and then CH3. So now let's look. What I like to do here is I look backwards. So what I mean by that is I look at this CH3. I know this has to be a 3H with 2 plus 1 is going to be 3 peaks. So that CH3 is represented by this thing, right? Now this CH2 right here, right, is going to be a 2H, and then it's going to be 2 plus 1 times a 3 plus 1. So that's a 3 plus 4. So there's a multiplicity, right? I mean 3 times 4. Right. So I know it's a multiplicity, and this thing is a multiplicity, right? Now I assume that there is CH2 here, which I should have not. I should have seen a multiplicity and just left it alone, right? Anyway, so it's a multiplicity peak, so I'm just gonna write MP. So that's represented by this one. So let me just use another color. Let me use orange for this one. So that's represented by this one. And then let's look at this one. I know it's gonna be a 2H with a 3 peaks, right? So let me use the pink color. CH2 is gonna be represented with this one. And the reason why I said that this CH2 is going to be connected to the oxygen, number one, is that the CH2 is not a multiplicity. So if this one was connected another CH2 to the other side, that would have a multiplicity like the orange one. But because it doesn't have a CH2, now someone might say is that, oh, it could have been like this, right? Benzene ring, an oxygen, a C double bond O, a CH2, a CH2, a CH3. Now, if that would have been the case, those peaks would have not been as downfield as they are. They would have been probably a little bit more upfield as compared to just having an oxygen next to it. So that's a little bit hard to notice. That's why you should look here a little bit into the CNMR, but like you don't really need it. But you can see here this represents the ester, which is the C double bond O. And all of that you can, I don't know if she's gonna give you the charts. I think she will, but I don't usually look at the C13 NMR because it just makes it a little bit more confusing to you to be able to figure out the problem. So that's why you'll be able to figure out. And as you see, this carbon did not have any H peaks. The reason to why is because it doesn't have any hydrogens. And then finally, this benzene ring is represented by those 2H and 3H peaks, right? Well, I hope it did make sense. Now, after that, we're going to be moving on to the multiple choice questions, all right? All right, so now working on the last part of this review session is going to be the multiple choice. I think I have like 5 questions ready. I'm mostly focusing on like IR, spectroscopy multiple choice question because I believe that this is what she's going to mostly focus on. So, first question is, which reagent will best accomplish this transformation? What happened here is that she started with an alcohol and we end up with an aldehyde. Remember, guys, when there's a CHO like that, this is an aldehyde. So, in other words, if I want to draw it out, it's going to look something like this. First step first is NABH4. If you guys remember, NABH4 is a reducing agent. So there's no way we're doing that, right? Because we're oxidizing, right? Remember, when we're oxidizing is we're increasing the bonds to oxygens, and we are minimalizing the bonds with hydrogens. So that's what reduction. Oxidizing is the opposite. Reduction is the opposite, is having more hydrogen bonds and less oxygen bonds. So NABH4 is a reducing agent. So NABH4, Allylic 4, those two are reducing agents. You should know that. Now looking at B, we're used to seeing Na2Cr2O7, if you guys remember, but they're both the same thing. Na2Cr2O7 or K2Cr2O7, they're both the same compound, and we also call them the Jones reagent. Jones reagent. This reagent is an oxidizing reagent, and it's not just an oxidizing reagent, it's a strong oxidizing reagent. So what's gonna happen here, it's gonna take a primary alcohol all the way to a carboxylic acid, so COOH, and a secondary alcohol to a ketone, so C double bond O. So that's the typical Na2Cr2O7 Jones reagent. That's the same thing. Now KMNO4 in heat is also an oxidizing agent, and it's also a strong oxidizing agent. It's gonna take it from a primary alcohol all the way to a primary alcohol. It's gonna take it all the way to a carboxylic acid. No, there's another oxidizing agent that they don't mention here, and the one that I want to mention is the bleach, NaOCl, and that oxidizing agent is this oxidizing agent is what do we call it? This oxidizing agent reacts with a secondary alcohol but not primary alcohol. So bleach oxidizes secondary but not primary, unless the primary is, and it oxidizes the secondary alcohol all the way to a ketone, right? So and the only way it can react with the primary is that if it is what's it called, conjugated. So what I mean by that, by conjugated, is like it's in a benzylic position, so it will look something like that, and there's no H right here. Then in this case, yes, it will oxidize it, and it's strong oxidizing agent. It's gonna take it all the way to a carboxylic acid. Now this is bleach, right? NaOCl. This is what sometimes when you put it on your clothes, you'll lose the color, and the reason why we lose color is because this bleach oxidizes the colors on our clothes, and then it turns them white, right? It loses its frequency. Now looking at the last one, now we're not used to seeing this thing. We're using to see PCC. PCC is a weak oxidizing agent, and it takes primary alcohols all to an aldehyde. That's the major difference between these two, between this oxidizing agent and like Jones or KMNO4. So you should also know the structure of it, because she can give you the structure without the PCC, so you should be able to recognize that structure for PCC. So in this case, because we went from the primary alcohol all the way to an aldehyde, that would be, my answer would be D. Alright, so let's look at this problem, and this problem is asking us to see how many sets of protons will be observed in the HNMR spectrum for this compound. So when we ask this question, we're like technically looking for how many unique hydrogen we can find. So a common mistake that I see happening in those type of questions is people will count those two hydrogen on those two carbons and the hydrogen on this carbon as being the same, but they're not actually the same. The reason why is that is because this carbon that has the hydrogen is connected to an oxygen, but this carbon is connected to the benzene ring. So those four hydrogens that are connected to those carbons are actually all unique. So that means I have, as of right now, I have 4 unique carbons. Now I have to look at the benzene ring, because remember, this benzene ring also has a hydrogen on each carbon. These two obviously they don't have because they're fully occupied. Now when looking at those two, we have to see that there's a symmetry here. So if you look at this carbon right here and this carbon, the 2 red carbons, they both have the same connectivity, meaning that those 2 hydrogens are actually not unique. Those 2 hydrogens are the same. The same thing. So if I look at this one, let me just say a little bit more. This carbon is connected to this carbon, and this carbon is connected to this carbon. Same thing with this one. They have the same connectivities. So, and usually you'll see that in either benzene rings, or you'll see that in the linear compounds with this plane of symmetry in the middle. So keep these in mind. Same thing with the other side. So same thing with these two carbons right here. They have the same conductivity, meaning that those two hydrogens are the same. So I will have to count those hydrogen once. So what I mean by that is this is one hydrogen, two hydrogen, 3, 4, 5, and 6. So I have 6 unique hydrogen that will show on my HNMR spectrum. Alright, oh my bad, I was solving this earlier on. Alright, so right here, they're asking us which compound is consistent with our spectrum. So before I look at the compounds that they gave us, I'll have to look at my peaks. What I can see from those peaks is I can see that there is one peak right here at about 1700. This peak right here represents my carbonyl. C double bond O. Now, anything after 1500, again, this is fingerprint region. This is just some noise and stuff. Maybe there's some some peaks that can help us, but it's really hard to identify them. So for that reason, what we have to know is that the only thing that we have is a double bond O, and if we go now one structure at a time or one compound at a time. The first one, A, they have an alcohol. And if it was an alcohol, we should see a broad wave at about 3300. So it will look something like that. At 3300, there should be a broad wave. But we don't have that, so we know it's not A. Now, let's look at... And let me skip B, actually. Let's look at C. If we look at C, we do have a carbonyl, which we do, so that matches. But if you look here, we have an NH2. Now, if you have an NH2, you always gotta have two peaks at around 3400, and that would be like this. A peak like that and a peak like that. We don't have those peaks in my IR spectrum, so that means it's not an NH2. So those are just values that you should... I think she will give you the table, but if she doesn't, with enough practice, it becomes like nature, and you'll be able to like recognize them. Now, moving to D, we have a carbonyl, which is correct, and we have an OH. But remember, in my IR, I don't have any OH spectrum, so it cannot be D. And the only answer that I'm going to end up with is going to be B. And the reason to why is that because it's the only one that has only a carbonyl. Alright, so let's move on. So what effect does the conjugation of a carbonyl group with a carbon-carbon double bond have on the infrared absorption due to the C double bond O stretch? So when we're talking a conjugation, I'm just going to draw an example. So we're going to draw like a example. Okay, random molecule. Double bond O here, double bond O here. So that... Looking at this, we'll see that we can see this double bond, single bond, double bond, right? That conjugation, if you guys remember from earlier on, this conjugation is actually something that is really stable, right? This thing stabilizes my molecule or my compound. And remember when I mentioned before about energy and frequency. So if we remember from Gen Chem or physics, energy is equal to H, Planck's constant, times the frequency. So the lower the energy, the more stable the compound is. More stable. And because energy and frequency are proportionally correlated, that means that as the energy decreases, the frequency also decreases. Right? I want to go a little bit further and explain how to correlate that to frequency. And I mean to wavelength. And as we know also from like Gen Chem or Gen Physics, we know that the frequency is equal to the speed of light divided by the wavelength. So as the frequency decreases, because they're inversely proportional, the wavelength will increase. I'm going a little bit beyond what this problem is asking for, but I think it will help you guys for if she gives you a little bit more conceptual questions. So now that we mentioned the wavelength, and if you guys remember in IR spectrum, she asked us always about the wavelength number. And the wavelength number is usually 1 over lambda. Right? So technically, the wavelength number and the frequency are proportionally correlated. I just want to say that. I think it's kind of helpful to think about it this way instead of just, memorizing. Anyways, so if we look at this problem, they ask us about the frequency, right? So something that is more stable, we said it has a lower energy because it's more stable, so the frequency is lower. So the first one says it shifts to a lower frequency, which we did correctly. And she said that we'll have a longer wavelength, which also matches with our second formula. So as the frequency decreases, the wavelength increases because of that inversely proportional relationship. So the answer would be A. Now, for this is the last multiple choice question that I'm going to be going over. Which reaction is best suited for the preparation of the ether shown? So there's a couple of conditions about this ether formation reaction that you guys learned in class. Is that, as you remember, that you want to have your halide on a primary carbon and your O minus that you're going to be using on it doesn't matter, right? It can be primary, secondary, or tertiary. The reason to why is that because this is an SN2 like reaction, and other than that, an E2 reaction will occur, and we don't want that. So knowing that condition, what I like to do on those problems, and I think you guys should do it during the test too, when she gives you like a condensed formula like that, I would always draw it out because I think it's easier to see. So it's C connected to CH3, CH3, and then CH3. And then this carbon is connected to an oxygen, which connected to a CH2 and a CH3. Right, so to form an ether, we know that we should be able to break this bond either here or here. But there is only one way we can break that bond. And I'm going to go throughout the multiple choice that we have and then figure out the answer, right? So, let me see. So for A, they gave us that C connect to CH3, connect to CH3, connect to CH3, which is connect to Br, plus CH3, CH2, O minus. Remember, this is just an ionic bond just to stabilize a negative charge. So that just, oh my god. So that's just going to be a K plus. So in this case, this cannot come in and attack this carbon, right? Because this is a tertiary bromine. So an SN2 reaction won't occur. Remember, SN2 favors primary over secondary over tertiary. Tertiary never happens, actually. So what would happen here is that this base is going to come in and grab, well, this O minus is going to come in and grab a hydrogen and then kick off the electrons, form a pi bond, and then the Br would leave, and then you'll form an E2 reaction. And that's not what we want. This is not our final product. So that would be an E2 reaction. That's not good. Now let's look at the second one. We have a CH3CH2 MgBr, and we have an alcohol. That would not work also, and we'll see why. So we have a CH3, CH2 MgBr, CH3, 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 and then we have an OH. In this case, nothing's gonna happen. The reason to why is that because this is a nucleophile right here, and this OH is also a nucleophile. They're both like, OH is not that good of a nucleophile, it's partially negative. So they're both nucleophiles. We don't have anything that's like partially positively charged to be able to attack it. So there is no reaction that's gonna occur here. No reaction. Now now for the option C, we have a CH3, because remember when we have, I'm going back to here, so if we have an MgBr, we should have also a carbonyl carbon. The reason to why we need a carbonyl carbon, because by induction it's gonna like suck the electrons, which make the carbon partially positive, and that's why we have a Grignard reaction. Now looking at C, we have a CH3, CH2, Br, plus C, CH3, 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 and then we have an O minus. This reaction would work. We have our condition, which is a primary halide, and it doesn't matter for the O minus. We just make sure we have an O minus, which is a strong. So what's gonna happen is this O minus is gonna come here, attack this carbon, and kick off the Br, and then we're gonna end up with a CH3, CH2, O, CH3, CH3, and CH3, which is matches what my result is right here. So that works. So the answer is C. And so that's pretty much it. This is the condition about this the formation of an ether. Be sure to be careful of it, because again, she can trick you. So see how like some people think that this is a primary on this side without noticing that there's 3 methyls connected to it. Just be careful. She will drop like tricks like that for sure. She always does this stuff, right? And that's why I thought this question is really good for practice, because this is a common mistake. Again, like I remember on my synthesis question when I took the test, the synthesis was to form an ether, and lots of people fell for the trick, and they put the halide on a tertiary and the O- on a primary. So make sure you know where you have to break the bond, right? So yeah, that's pretty much it, guys. Good luck for the final. I'll probably hold like a live review session a couple days before the test. All right. Good luck, everyone.